Hello and welcome to this video about the electrolysis of aqueous salts. In this video we're going to look at how the electrolysis of aqueous solutions is different from the electrolysis of molten salts, and this also relates to required practical 3, so we're going to look at what would be required for that. So first of all, a reminder about the definition of electrolysis. Electrolysis is the breaking down of a molten or aqueous ionic compound using electricity. In the previous video we talked about why it's important for the ionic compound to be molten or aqueous, i.e. in a liquid form, so that the electrolyte conducts electricity. And we focus on what happens when you pass an electric current through a molten ionic compound. Now we're going to look at how an aqueous compound is different. It's still an ionic compound which therefore contains a positive and negative ion. However, because aqueous means dissolved in water, we're also going to have the water ions in there, and water breaks down into H+ and OH-. So in aqueous solutions, we're always going to have the positive and negative ions from the ionic compound, and the H+ and OH- ions from the water. And that's what makes it slightly more complicated, because only one of the positive ions and one of the negative ions can form at each electrode, so we have to predict which one will be formed. So, let's focus on the cathode first of all. Because the cathode is negative, it's the positive ions that will be attracted towards it. So to figure out what's going to be formed at the cathode, we need to focus on what positive ions are present in the solution. So if we have a solution of NaCl, that's sodium chloride, the positive ion in this compound is the sodium. So one of the ions present is sodium, which is a 1+ because it's in group 1. And of course, because we have the water, we also have the H+ ion. Now let's look at the rules. We know that the element formed at the cathode will either be the metal from the ionic compound or hydrogen gas made from the hydrogen ions. But what we don't know yet is that the least reactive element will be formed. So in order to decide which of these elements is going to be formed at the cathode, we need to refer back to the reactivity series. Here is hydrogen in the reactivity series. So if the least reactive element is formed, and we have any element above hydrogen dissolved in water, that means that the least reactive element is hydrogen. So in this case, sodium is more reactive than hydrogen, and so the least reactive element is the hydrogen. So hydrogen is going to be formed at the cathode. You'll observe this as bubbles of gas, and if you want to test it to make sure, we can test it with a lit splint, and it should produce a squeaky pop. Now that we've looked at one example, see if you can work out the positive ions present in the other 3 examples and what the element formed will be. Have you worked it out? Okay, so looking at copper sulfate, we should be able to see that the metal ion is going to be the copper ion, and you might not have known, but copper is normally a 2+ ion. If you're not sure, you can work it out because it's attached to the sulfate ion, which you need to remember is a 2- ion. The compound has to always be overall neutral, and so if the sulfate ion is 2-, that means the copper ion is 2+. So we've got the copper ion and we've got the hydrogen from the water. Now we refer to the reactivity series and we can see that copper is less reactive than hydrogen, so copper is going to be formed at the electrode, and this will usually look like a brown coating on the electrode surface. Magnesium is a 2+ ion. We know that because it's in group 2. And we'll also have hydrogen as the other positive ion. Looking at the reactivity series, magnesium is higher than hydrogen on the reactivity series, so hydrogen is going to be formed. And here we have silver, which is Ag1+. Again, you might not know this from the periodic table because it's not in group 1, but it's attached to bromine, which is in group 7, and therefore has a -1 charge. This means that overall, to make a neutral compound, the Ag must be 1+. So we have the Ag, the silver, and we have H+, which is the hydrogen. Looking at the reactivity series, silver is less reactive than hydrogen, so the silver must be the element formed. So you can see here that if the ionic compound contains a reactive metal, then hydrogen will be formed at the cathode, and if the ionic compound contains a less reactive metal, then the metal itself will be found at the cathode. This is actually related to 2 important uses of electrolysis. One is for purifying metals such as copper or silver, and the other is for electroplating items such as spoons or jewellery, with silver or gold or other precious metals. Great, now let's look at the anode. So, at the anode, we're always going to produce negative ions. This means it's either going to be the negative ion from the ionic compound, or it's going to be the hydroxide ion from the water. This can be summarised into three main categories of ions. We've got the halogens, which are the group 7 ions, such as fluoride, chloride, bromide, or iodide. The hydroxide ion, or other negative ions, and these might include, for example, sulfate or nitrate. So let's have a look at what would be made in each of these examples. So, in sodium chloride, the negative ion present is of course the chloride ion. That's Cl-, 1- because chlorine is in group 7 and that means it gains one electron to get its full outer shell and so has 1- charge. Then we also have the hydroxide ion from the water, OH-. To figure out which element is formed, we use the rule as above. If we have a halogen present, it's going to be formed, that's the priority. If there isn't a halogen in the compound, then the hydroxide will be attracted to the anode, and it will produce oxygen gas and water, as we'll see in a bit more detail later. So this is the second priority. If there was a case where we didn't have a halogen or a hydroxide, then the other negative ion would be attracted to the anode. However, because this is aqueous solutions which are always dissolved in water, we're always going to have the hydroxide. So really we're just focusing on the idea of whether or not it has a halogen. So in this case, chlorine is a halogen. So a halogen is going to be formed, and in this case, chlorine as an element is Cl2. Before I go on, have a go at the rest of them yourself. Click pause, and when you're done, press play again to see if you were right. Have you done it? Well, in copper sulfate, the negative ion present is sulfate, SO4, 2-. And of course we have the hydroxide as well. So if we go up to this order of priority, we can see that we don't have a halogen, so the hydroxide must be formed. That means that we have oxygen and water produced at the anode. It's not always necessary to write the water, because that will actually stay in the solution. Oxygen gas is what we would observe as bubbles and what we can test if we wanted to. The next one, magnesium nitrate, well, this contains nitrate ions, NO3-, and of course the hydroxide ions. Again, like the one above, it doesn't have a halogen, which means the hydroxide is attracted to the anode and we get oxygen and water formed. And finally, silver bromide. Well, we're going to have a bromide ion. Again, bromide is in group 7, so it produces a 1- ion. And we have hydroxide. Because bromide is in group 7, that means it's a halogen. So a halogen is formed, and that's going to be bromine, Br2. You may also be expected to test for these elements. All of these elements produced at the anode are gases, so we're talking about tests for gases. We go into this in more detail later on in topic 8, but let's briefly cover it now. If we have a halogen, it will bleach blue litmus paper. So to test for it, we dampen the blue. We make the blue litmus paper damp by dabbing it in water, and then we hold it over the gas that's being produced to see if it bleaches, which means turns white. Occasionally it turns red before it turns white, but if it's a halogen, it will always bleach it. The other gas that we're looking for is oxygen, and to test for oxygen, it should relight a glowing splint. In order to do this properly, you should collect the oxygen in a tube and then make sure that none of it escapes. And when you have enough, you insert a glowing splint and it should reignite. This is pretty much all you need to know about electrolysis of aqueous salts if you're on foundation tier. But you do also need to know about the required practical for this topic, which is all about identifying the elements produced at each of the electrodes. So we've already covered most of the information needed to do the required practical. You'd be expected to be able to set up a beaker like this with the electrodes connected up to wires using crocodile clips. And then you do that with each of these 4 solutions and test the products. First of all, see if you can remember from the last couple of slides what you might expect to see at each of the electrodes, and what element would be formed. Pause the video and come back when you think you've got as much as you can. So for the copper chloride, we're going to have a gas produced which will look like bubbles. This is because the chloride ion is attracted to the positive electrode and forms chlorine gas. We can test this using damp blue litmus paper. Can you remember what happens to it? It bleaches, which means it turns white. Okay, in the copper sulfate we'll also have a gas or bubbles, but if you remember from the previous section, the sulfate is not what's produced. It's the hydroxide that's attracted to the anode, and therefore we get oxygen gas. Do you remember how to test it? Oxygen gas should relight a glowing splint. It's worth remembering that water is also formed here, but it's unlikely you'd ever be expected to mention it in this context. With the sodium chloride, again we're going to have gas bubbles of chlorine produced, and with the sodium sulfate we're going to have gas bubbles of oxygen produced. Did you get as far as predicting what would be produced at the negative electrode? If not, pause the video and have a go now. Right, well both of the first two involve the metal copper. So because copper is less reactive than hydrogen, it's the copper that's going to be formed. This looks like a reddy brown solid that coats the cathode, a bit like this. For both sodium chloride and sodium sulfate, we've got the metal sodium, and of course the other ion is hydrogen. So because sodium is more reactive than hydrogen, we know the least reactive element will be formed. So for these two, we're going to have hydrogen produced at the cathode. This will be observed as gas bubbles. And do you remember how to test for hydrogen gas? If you collect enough gas in a test tube and you insert a lit or burning splint, then you'll get a small squeaky pop, and this tells you that hydrogen is present. If you're on foundation tier, skip the next few minutes that are about half equations because you don't need to know about that. But don't forget to see the end of the video where you can test your understanding with a few questions and remember the keywords that we used in this video. So for higher tier, as well as predicting what element is going to be formed at the anode and the cathode, you also are expected to be able to write the half equations as you did for molten compounds. So in this example, we're going to be doing the electrolysis of sodium chloride. We've already looked a couple of times at what would be produced. We know that at the cathode, we're going to have hydrogen formed, if you remember from earlier. At the anode, we're going to have chlorine formed, because it's a halogen which has the first priority at the anode. So let's have a look at the half equations. At the anode, we start off with the chloride ions in the solution, and we make chlorine gas, which is Cl2. We've got two chlorines here, but only one here, so we need to balance it with a big 2. And remember, we need to balance the charges as well. We now have 2 negative charges, which means over here we need 2 electrons to balance out the negative charge. And there's the half equation for the reaction at the anode that produces chlorine. At the cathode, we have hydrogen. So we start off with the hydrogen ions, and because these are positive ions, we must gain electrons to form the element. The element in this case is hydrogen gas, which is H2. There's 2 hydrogens here. We need to remember to balance this side of the equation as well. So we have to put a 2 here and a 2 here to make sure we've got the right numbers of hydrogens and the right balancing of charges. And it's as simple as that, really. So let's see how much you've understood. In this example, we're going to be electrolyzing copper sulfate solution. Can you tell me what element will be formed at each electrode? Which ions will be left behind in this solution? And if you're going to do higher tier, can you write the half equations for the reactions at each electrode? So to answer the first question, it's important that you're clear what is formed at which electrode. So make sure you name the electrode as well as the element. So if we start with a positive electrode, you could say positive electrode, or you could call it the anode. we're going to have the negative ion forming an element. So in this case of copper sulfate, to work it through, we should figure out first that we have the sulfate ion, SO4 2-, and the hydroxide ion, OH-. Using the order of priority from before, we don't have a halogen, but we do have the hydroxide, and so the hydroxide is going to be attracted to the anode. This is going to form oxygen, which is the element formed. And at the negative electrode, which is the cathode, we're going to have either the metal copper, because we've got copper 2+ ions, or the gas hydrogen, because we've got the hydrogen 1+ ions. So we need to compare their reactivity from the reactivity series, and copper is less reactive than hydrogen, so copper is going to be formed at the cathode. So if oxygen is formed from the hydroxide and copper is formed from the copper ions, which ions will be left behind? Well, of course, that's going to be the hydrogen ions and the sulfate ions. If you're really switched on and you've recently learnt about acids, you might recognise that these two ions are the ions that make up H2SO4, which is sulfuric acid. This means the solution at the end is going to be more acidic than it was at the start, because it has all these hydrogen and sulfate ions that make up sulfuric acid. This would be a really hard question in the exam, but it's worth pointing out here. Finally, if you're on higher tier, you need to be able to write the half equations for each of the electrodes. We know that we'll start with a hydroxide ion, OH-, and we're going to make oxygen and water. Okay, now we need to make sure we balance it and have the right number of electrons. So we'll add a 2 here, which means we have 2 oxygens now, plus 2 there, which is an overall number of 4. So we'll put a 4 here to say we've got 4 oxygens. This means we have 4 hydrogens as well. So if we have 4 hydrogens, we've already balanced it. 2 times 2 is 4, so we have 4 hydrogens. So we've balanced the number of elements now. We just have to make sure we've got the right number of electrons. So on this side we have 4 negative charges. So we need to make sure we have 4 negative charges on this side as well. 4 electrons. And that's the half equation for the hydroxide forming oxygen and water at the anode. At the cathode we have the copper ions, Cu2+, and they make copper metal. In order to balance the half equation, we've got the right number of coppers already, but we need to balance out the charges. With this 2+, we need to add 2 electrons to this side so that we have the same charge on either side. 2+ and 2- makes a neutral charge. Well done if you've got those right, and that's it. Finally, here are the keywords for this video. This is the last video for topic 4 chemical changes. Thanks very much for watching, and hopefully see you again on the next section all about energy changes in reactions.